Good morning. Welcome to the show. My name is Chris Coe. I'm integration engineer at Off-Chain Labs. We were the initial creators of Arbitrum, and we now act as service providers for the Arbitrum Foundation and the DAO. And today we're going to talk about this is a third in our series about how to do about Arbitrum Stylus. And today we're going to talk about the title of this talk is how to save millions in gas on the $1 trillion equation with Arbitrum Stylus. So, what is the $1 trillion equation? We'll get into that, but first, just want to kind of recap a couple of things. So, um, just yeah, again, my name is Crisco, and if you need to contact me, just those are my socials. I'm on Twitter or Telegram at Crisco512. But just to kind of recap what we covered last Wednesday, Jose was presenting and he presented on how to test Rust contracts, went over the unit testing framework with Matsu, how to do integration tests, also covered cargo stylus tools like caching contracts and tracing transactions. If you missed that, feel free to go back and watch that on the Arbitrum channel. I think we'll post the link in the chat for those, and on the X Twitter account as well. But yeah, good presentation, and the intro one from last Tuesday also good to catch as well if you didn't see any of that. But today we're gonna go over more of a even though the first example was a first day on this was about sort of like an intro to Stylus and how our frameworks work. And then we also went into on the second day testing and more debugging and those types of things. And then today we want to go over more of a practical example of why Arbitrum Stylus is a powerful tool to use in on-chain applications. And so today we're going to cover an advanced financial calculation called Black-Scholes, and it's a well-known equation in finance, and we're going to explain why Stylus enables advanced on-chain finance among other applications, right? I mean, so basically Stylus allows the reason why we're able to do more advanced math and computation on chain is because we're working in a WebAssembly VM context that we've created that works parallel with the existing EVM in Arbitrum chains. So we're able to get access to more than 70 times more compute and 1,000 times more memory per unit of gas versus Solidity. And what this does is this unlocks the ability to do just more powerful on-chain applications. That includes cryptography, includes gaming, includes art, includes finance, anything where additional compute can be useful. You can see a lot of benefit from Stylus. So we're going to show this equation has been probably impractical, if not impossible to do. I did make an attempt to implement this equation in Solidity and I was unsuccessful. Maybe somebody out there has done it, but I'm sure that if it's done, it will cost millions in gas. And so what we're going to show is how this is significantly cheaper and significantly more feasible to run on chain than what's possible in the EVM and Solidity. So yeah, this is just yeah, very exciting stuff. And so just to cover what we'll cover during this presentation, I'm gonna give you some context on Black-Scholes and what it's useful for. And I want to start by it's basically used for options contracts. And I want to start by talking a little bit about the history of financial markets and options themselves. And then I want to go into like the formal developments of what led up to the publication of the Black-Scholes model in the 1970s. And then I'm going to show the equation, explain some of the math behind it. Like I don't want to get. I mean, I'll get deep enough where you you'll probably be able to like if is this your first time hearing about Black-Scholes, you may not be able to follow 100%, and like it may some of it may go over your head. It took me several times reading through Black-Scholes to really kind of grasp it, and that's totally normal and understandable. For today, you don't have to, like, worry too much about understanding it. I will explain enough where, especially if you're familiar with it, you'll get a refresher on it, and if not, you can rewatch this or reference some resources online to, like, learn it in a better detail. But what I'll do is I'll explain the math, and then I'll go into showing how to implement that math in Rust, and you'll see, at least you could see that even if you don't understand the math behind the equation, you can at least see that with a complex differential equation like Black-Scholes, how you can practically do that in Rust and how you can do that on chain, and execute on that. So don't worry if you're not able to follow 100% with the math, but it will, obviously, if you have like a finance background, it will be helpful. But if not, it's okay. Just bear with me. I'll try not to get too deep in the weeds on that stuff, and we'll demo that contract and show you how much gas it actually costs in practice. So first, this the title of this says, "What are the options?" But I just said, what I meant to just say, "What are options?" So options are financial instruments to give the buyer the right, but not the obligation to either buy or sell an underlying asset at a specific price. We call that price the strike price. And you have, with options, you have a certain amount of time to exercise them, and that's called the expiration period. Um, a lot of times that can be 1 year, it could be a 3-month contract. Um, for this demonstration, we'll just be sticking with 1 year. So usually when you buy an option contract, or traditionally when you buy an option contract, it might have a 1-year expiry. Um, Not all options have 1-year expiries, but for simplicity and for this talk, we'll just stick with 1 year. Um, there's 2 different primary types of options: the call option and the put option. Calls are the right to buy an asset. The holder of a call option expects the price to rise above the strike price. Um, so that is to say that if I buy an option and it has a specific strike price, I'm betting that the asset will rise above that strike price, um, by the expiration date on the option contract. And with the put, it's sort of the opposite, but it's the right to sell an asset at a specific price. And put options are, you're expecting the price of the asset to fall below a specific price. Today, we're going to stick with call options. The original Black-Scholes is based on call options. It's still used to compute put option prices as well, but for simplicity, we'll stick with call options for this presentation. What are some of the benefits of doing options? You've got access to leverage. You can move a lot more money with options. You can manage your risk better. You can hedge your bets, and you're basically you've got unlimited upside but limited downside on options, right? So the total cost of the premium is your maximum loss for the option contract. There is a limited time frame in which to exercise those options. So if the asset, maybe you're right that the asset will go up in price, and so you buy a call option, but maybe it happens, after your expiration period. That is like one of the risks that you take with call options. So it's just something to keep in mind. It is a risky financial tool, just like anything else. Um, but it has proven to be useful in financial markets, um, with with and it's resulted in like multiple trillions of dollars being traded every day in current stock markets and commodities markets as well. Um, all right, so just kind of going back through some of the history, options as a concept, they've been around for centuries, even if the term hasn't been explicitly used. Um, they originated, well, the first recorded known example of an option was a man named Talus. Thales. I'm not sure how to pronounce ancient Greek names like that, but he used a form of options to secure olive presses. And that picture here is this is an ancient olive press, and he lived from 624 to 546 BC, and he would use basically he would track weather patterns, and then he would predict what the olive yield for the upcoming season would be. And if he thought that it was going to be a good season for olives, well before the harvest was ready, he would secure contracts to use other people's olive presses, and he'd pay them. He'd place a deposit for the right to use the press, but not the obligation. So he'd buy an option contract on the ability to use those presses during harvest season, and it turned out to be a very successful strategy. I think the combination of his prediction about the weather and the yields on the crops that year, plus the his foresight into securing the contracts ahead of time. Basically, whenever there was a good harvest, he would have sort of a monopoly over all the presses in the city, so he could use that leverage. A lot of times he would just re-rent the presses out to people that desperately needed them because they have more olives than they knew what to do with. So he was able to like use that and dominate the olive press market as a result. But there were other examples throughout the centuries, champagne fairs in France, where merchants would secure options to buy goods for those fairs well ahead of time. These fairs were like big, semi-annual events that, merchants would sell like wine and goods and things like that. And so, merchants would use these option contracts in order to make sure that they had supplies, if there was a good turnout. Uh, in the 17th century, London, England started to formalize more options in their financial markets in London at the time. And so you'd start to see what they called refusals and privileges being traded at the time, mostly involving agricultural commodities, wheat, corn, etc. Um, in the 19th century, we started to see over-the-counter trading in both New York, Chicago, well, in the U.S. and in England at the time. New York, Chicago, and London being the primary cities for those trades. And to this day, those cities remain important markets for options trading. Um, so, the lack of standardization, there were problems with the old markets. The lack of standardization made trading options very risky, made it very not very accessible, and it was largely just based on intuition. Like up until the late 20th century, we're talking 1970s, it's mostly intuition that's guiding the pricing of these contracts, right? Everyone recognizes that options can be a useful financial tool, but because of the inefficiency in how to price these things, they really just didn't, they really never took off as much as they do to modern day, because yeah, because it was very illiquid. Things had to be traded over the counter, so it was just like you were almost like negotiating with farmers directly. There was not, a lot of it was a lot of friction to make an options contract happen prior to the 1970s and the establishment of options exchanges. So, a lot of people started to, in the 20th century, started to formalize more financial theory. So there's a couple of developments that happened in the 20th century that enabled us to get to the markets that we have today, and kind of started off with with a paper called "Theory of Speculation" by Louis Bachelier. And he modeled stock prices in that paper as a random walk, and what you see what's interesting is that right around that same time, around that turn of the 20th century, right, very beginning of the 20th century, there were also developments in physics to model random walk type of phenomenon. And what we call Brownian motion, which is what you're seeing in this GIF here, you're seeing like basically sort of a model of random pollen particles banging against each other in fluid. And you might try to model the movement of a single particle within that, um, within that collection there. And to do that, it requires advanced math. And Einstein was one of the first ones to sort of like model this behavior to create a mathematical model to model this random walk. And he used that to, to prove the existence of atoms. So at the time, they were still debating whether atoms existed or not. And it's interesting that both like this is one of the rare cases where these two completely different fields were able to like sort of lean on the same. I mean, maybe it's not so rare, but to lean on the same idea of like random walk movement and Brownian motion, both to model phenomenons in nature, but also to model financial markets themselves. Um, and then towards the 60s, there was more theories about the markets and the so-called efficient market hypothesis, which basically hypothesizes that markets eliminate arbitrage rather quickly when they're efficient. So that it this is a it's important to note that this is sort of a theoretical framework. Like financial markets are informationally efficient. One can't consistently achieve returns. The theory is that one can't consistently achieve returns in excess of the average market returns on a risk adjusted basis. It states that the markets react instantly to new information, and um, as a result, this leads to a random walk of stock prices, sort of like, you can't be more certain that the price of something's going to go up than you can that it's going to go down. We certainly see this in crypto markets. You can't predict. I mean, as much as people try to predict movements based on charts and things like that, based on technical analysis, you can't know with certainty whether an asset will go up or down. It does have an element of randomness to it. That certainly can be said for crypto markets and financial markets in general. Um, Towards 1973, arrive at the publication of Black and Scholes were associates, and they had developed a model in the late 60s that they published in 1973. And then Merton, who had separately worked on a similar concept, contributed a little bit and helped refine their model a little bit. But right around 1973, we get that publication of how to price options contracts that uses some of these like Brownian motion and efficient market hypothesis, and it combines it into a nice, elegant formula that changes the game with options and allows financial experts to analyze whether the price of an option was a good deal or not. And that helped to make the options markets just more efficient. So, right around that year, 1973, Chicago Board of Options Exchange was founded, and we see this significant shift in financial markets, right? The Chicago Board of Exchange Options Exchange was initially resisted by the SEC, so that may sound familiar for some people in this industry, but the formalization of options pricing meant that this resistance would not last. So since Black and Scholes published this like formal method of analyzing options right around the same time as CBOE was founded, the SEC basically had to relent and show that this is a legitimate market and that this can grow, and this is not just raw speculation, but something useful that can be analyzed in a predictable way. Right after it was founded, by year 3, it had already grown by like it started off with 35,000 contracts. By year 3, it had risen to it had risen to 1.5 million contracts. So it was growing exponentially even in the first 3 years and continued to grow to this day where over 1 billion options are traded every month on the CBOE alone. That's not counting other foreign markets or digital markets. So over $40 trillion in volume is done um, every month in these markets. These markets are huge. And so when we call the Black-Scholes the trillion-dollar equation, this is what we mean. It's helped to spawn multiple trillion-dollar markets in the just derivatives in general. Like options were the first derivatives market to go mainstream, but other derivatives markets exist as well. And so it's been a hugely impactful thing, and the last 50 years of finance have been hugely impacted by these developments. Okay, so let's go into a little bit more about the theory of black souls and how it works. So again, kind of reiterating that the key assumptions are these are theoretical assumptions. They don't align with reality perfectly, of course. Everything's simplified to make the math easier to compute. Obviously, the real world doesn't work this way in practice, but it's better than guessing in the dark or just using your intuition and guessing whether an option's at a good price or not. So um so with this simplified model, it's also important to note that this model's been modified in modern times to a large extent. Like in practice, financial experts will use heavily modified models to um to model modern markets. But with these simplified assumptions, we'll go over the Black-Scholes model as it existed in 1973. Um, the key assumptions are that the stock price follows a Brownian motion, a geometric Brownian motion, or a random walk. That means you assume that in any moment in time, it's just as likely that the price of the stock will go up as that it will go down. And we're using stock price, but this also applies to any underlying asset, whether it's a commodity, whether it's crypto, whatever it might be. Likewise, we're going to assume that there's no arbitrage opportunities. Those are quickly eliminated by the market. You have the ability to buy or sell an unlimited number of these options, that they're not in limited supply. We're also going to just eliminate transaction costs and taxes. We're not going to factor for those, although in real life you have to factor for those things. We're also going to make the assumption that all these securities are perfectly divisible. In crypto, a lot of times things are perfectly divisible, but in securities, a lot of times you can't really buy fractions of a share. Um, so we're just gonna, but to simplify things, we're gonna assume that they are. We're also gonna assume that the risk-free interest rate is constant and known. And the risk-free interest rate, I might be getting ahead of myself, but the risk-free interest rate is just this idea of an asset that is relatively risk-free. In practice, there is no risk-free asset or investment, but usually treasuries or T-bills are used as sort of a stand-in for that, because government securities are about the safest type of investment that you can make, because they have the money printer, so they can always print more money. And and we're also going to assume that there's no dividends if we're talking about stocks. We assume there's no dividends in the asset during the life of the option, just to again make the math easier. So we're just talking about buy price and sell price. Okay. Uh, Again, just reiterating over some of the definitions that we've covered and some that we may not have. Call options are the right to buy an asset at a specific price. Put options are the right to sell an asset at a specific price with by an expiration period. The strike price is the price for the underlying asset if the option is exercised. Again, an option is the right to either buy or sell an asset at a given price, but not the obligation. So you always have, if you have an option, you have the right to buy or sell it at that price, but um, not the obligation to. So if conditions change unfavorably for the option contract that you purchased, you just lose the premium, which is the price that you paid for the contract itself. Expiration is the date at which that contract expires. There are two traditional types of options that we talk about. There are so-called American options and so-called European options. Um, American options have the right to be exercised at any time before the expiration. So if you buy a 1-year American option, you can exercise the option 6 months in, 3 months in, 2 weeks in, whatever you want. If the asset moves into an to a good place at any point in the interim between the date you buy it and the expiry date, you're able to exercise it at any time. With a European option, you can only exercise those on the expiration date itself, not before. So if it's a 1-year contract, you have to wait all the way to 1 year to exercise that contract. Now, that's not to say that you can't resell or flip the contract itself. You might be able to do that where you get somebody else to take over the contract in the interim. That would usually be how you might liquidate a European option. Um, but you know, but you can always hold it to expiration and then exercise it at the expiration date as well. Um, the risk-free rate, I just covered that. It's usually a zero risk or low risk investment like government bonds or T-bills. Okay, so here's the actual formula. Again, like this is like gonna look a little intimidating, especially if it's been a while since you've done um, calculus or differential equations or but again, like I said, you don't have to. I'm gonna explain enough to give you an idea, rough idea of what's going on. But if you don't get this, just follow with me, stick with me, and then I mainly want to show you that this is a complex mathematical formula that we're able to translate to Rust, and then we're able to execute that in a reasonable amount of gas. That's gonna unlock advanced on-chain finance. So I just want to showcase that and follow with me, and we'll get through it, and you probably won't get it the first go, but that's okay. Um, there's plenty of resources to learn more about this formula if you're curious, but I do at least want to get through the idea that you can do advanced on-chain math that you probably would be scared to do in Solidity because you get a stack too deep error, like 10 variables in. So we want to showcase some of these advanced examples to show what the power of Stylus really is. Okay, so there's a couple of variables here that we've got to cover, and yeah. So okay, the C is the call option contract price. Okay, so we're computing what the Black-Scholes formula is computing is what the ideal price or what the fair price for a call option contract should be. All right. In this formula, you see S sub zero, or we could just call that S. Um, that is the current stock price. Again, even though we're using stocks, this applies to any financial asset. But we'll go ahead, since the original formula was written with stocks in mind, we'll stick with the original definition. The present value of the underlying asset. So that is the current price on the market for that asset. N is a concept in statistics called the cumulative normal distribution function. So when you see N, so you got S times the cumulative normal distribution of D1, which I'll explain on the next slide. Um, and again, you don't need to know this, but what that is a statistics concept. I guess like a normal distribution function computes what the likelihood that X within a range will be less than a certain amount. So it's a little bit hard to understand, but it's sort of a statistical probability function. Let's call it that. K is the strike price or the price of an underlying asset if exercised. Okay. So if the strike price, right? So if we buy an asset, like basically if the current price of an asset is $100, the strike price might be $105, right? So we got the option to buy the asset for $105 a year from now. And we're speculating that the asset price will be worth well over $105 one year from now. So we're locking in that $105 price because we expect it to maybe double, maybe it'll be 200 a year from now. So if we've got the option to buy it at 105 a year from now, we've locked in a big payday. Um, okay. The E symbol is Euler's number. That's 2.71828. I'm sure you've seen that in either physics or math somewhere. It shows up in nature all the time, and it shows up in financial markets too. Um, and that is raised to the power of the negative of the risk-free interest rate, which is the theoretical rate of return on a zero risk investment, and then that's multiplied by the time to expiration, which is how much time the option has left. If it has 6 months, if it has 1 year, um, and then that's all multiplied by the cumulative normal distribution of D2. All right, so D1 and D2, we've shown these two terms, but we haven't explained what they are. All right. So this first term, all right, basically just at a high level, right? The what we're doing is S is the S this first term right here, that's S times ND1, that is that term represents the expected benefit of acquiring the stock outright. And it can be interpreted as the present value of the stock that you expect to own if the option finishes in the money, adjusted for the probability that it will. Remember that cumulative normal distribution function is a statistical function that computes the odds that some x will be within a given range. And so this first term essentially is your the expected benefit of if this stock finishes in the money, how much profit could you make off that option? And then subtracting the second portion of the formula. Oops, let me click back. The second portion of the formula represents the cost of that option. So it represents the expected cost of buying the stock when the option is exercised. Okay. So by subtracting the second term from the first, we get the net value of the option. It's the difference between the expected value of owning it and the expected cost of acquiring it through an option. All right. Um, Let me go maybe a little bit further. Yeah. Yep. All right. Yeah. Let me go into D1 and D2. And yeah, so D1 breakdown. Okay, so then these look intimidating. And again, it's not something that you have to know in this presentation. I just kind of want to show that we're doing advanced math under the hood, right? So we've got a natural log function that we're throwing in here. Oops, oops. We've got we're bringing back the strike price and the stock price into this. We've got a new term called sigma, which is the volatility rate. This is something like, you know, this is something where you'd look at the historical volatility of an asset and you'd compute an estimate of how volatile you think that asset is. In crypto, it's highly volatile, so sigma would be very high. If it's something like the S&P index, the volatility might be a lot lower. In fact, there is a publicly traded index called the VIX that's based on the S&P 500 that is just computed for you that you can trade against as well. So volatility rates exist themselves as something that you can bet on or that you can build products around. So with Black-Scholes, we're assuming that volatility is consistent across the length of an option for simplicity of math. Um, but again, like to not get too deep in the weeds on the math itself. Um, this ultimately, again, D1 is meant to compute the expected benefit of owning the option if it finishes in the money, and D2 is essentially computing the expected cost of acquiring the option based on the changing conditions in the market over the period of time. Okay. So, yeah, um, yeah, this right, this is complex formula that's hard to grasp in, like, just a quick 1-hour presentation or whatever, but to to, um to kind of, wrap it up or to kind of, like, just showcase enough of it that I can go to the Rust and show you some advanced math and how we're not just making this up. This is, a formula that works to price options in a way that factors for randomness and factors for interest rates and the amount of time that you have to exercise that option and the probability that it actually finishes in the money. In other words, the probability that it's going to um, exceed in the case of a call option, it's going to exceed the strike price in um, by the expiration date. Okay. Um, cool. All right. So moving on, let's go to the actual Rust code so that we can talk about that, showcase that. So let me move my Safari window out of the way. All right. Okay, so now we've got over here on the left, I've got my Nitro, my local Arbitrum node is just running. I've already got it running. Um, and over here on the right, we've got this is only about 100 lines of Rust. Okay, so this is not a lot of Rust in order to implement the Black-Scholes equation. Um, I'm 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 not really cheating, but I'm taking advantage of a library called the Decimal Library. Okay, it's the Rust Decimal Crate. This is Rust Decimal that's published on crates.io, and this is a fixed point decimal library that helps us do this advanced math in Rust. And the reason why it's a fixed point library is because in Stylus and in blockchains in general, it's difficult to do floating point, right? We do need to do we frequently need to do division and things like that in financial applications, but it turns out that doing floating point can sometimes lead to non-deterministic behavior, where depending on the architecture that the node is executing on, like whether it's x86 or ARM, some of the like tiny decimal points of precision can vary between computer architectures, and so a lot of like in Solidity, you don't really have access to floating point, and currently in Stylus, you don't have access to floating point because we have to make sure that in a blockchain environment that things um, run deterministically to the last bit. So because we're proving over the state to the very last bit, we have to be very, very precise and careful. So we have to use what it's called fixed point math instead of floating point math. And fixed point math just it basically takes an integer of a specific size and it sets aside some portion of that integer for so-called mantissa, which is you might have seen like on your graph on your calculator, even if you've never done this in computer hardware engineering or software engineering, you might have seen where your calculator or a scientific notation where it might say 3.7 times 10 to the sixth or 10 to the negative sixth or something like that. Um, or you might have like uh, yeah, basically what you're doing is you're taking this mantissa, which is the number itself, and you're separating that from the notation that represents the number of decimal places that number represents. So when we use this library, this Rust decimal crate, we are we're allocating 128 bits for every number, and the mantissa is a number between -2 to the 96 and 2 to the 96, and E is an integer between 0 and 28. So it's basically saying you can have up to 28 decimal places for any integer that is between -2 to the 96 and 2 to the 96. And for a lot of applications, unless you're doing astronomical physics or something like that, it's 2 to the 96 is a huge number that is more than suffices for the vast majority of financial applications. So this library tends to work really well for us, and we're going to take advantage of it in order to use to do fixed point math equations on chain. All right. So, and it also gives us access to a number of like functions that we can use without having to implement those ourselves. Um, okay. So going into the actual contract logic itself, we're just gonna cover like the single compute function. This is the only public function that our contract has. So right now we've hard coded this. There is no parameters to this function. I'm just hard coding the price. The price is right in the code, but obviously we could make parameters here to allow someone to pass in the strike price and the call the asset price, the strike price, the sigma, etc. We could have all these be parameterized so that anyone calling it could customize it, but for now, we're just going to hard code these values and then show the computed option price. Okay, so we've got from the formula, if you remember, S was represented the stock price or the asset price. So we're going to just use 100 even as the asset price. We're saying that the asset price is $100 currently on the market, and then K is the strike price. We're betting that, in other words, it we're if someone were to buy this option, they'd be betting that the price would exceed $105 before the expiration period is up. We're also plugging in as a risk-free interest rate 5%. This is 0.05, 5%. And we're going to use just as an arbitrary volatility rate 20% as the volatility rate for that asset. In other words, it's likely that the price of that asset could go 20% up or down before the end of 1 year, which is the expiration period um, that this option covers. And we're going to compute. We're going to call this compute all function where we pass in those parameters. It's going to output, and we're going to use the Stylus debug console output to output the call price that we compute. And then we're gonna actually separate out the mantissa and the scale that I just talked about, and we're gonna return those values so that if somebody's calling this, I mean, we could probably like combine the mantissa and the scale since mantissa is only 128 bits technically, but we are casting it to an I-256, and the scale is also only 32 bits, but we're casting it to 256 bits. We could probably combine those into a single a single I-256 that we return. Um, if we understood, if the caller understood that they'd have to parse out part of that 256-bit integer to know like which part of the integer is the scale and which part is not. But for simplicity, we'll keep the mantissa and the scale separate and just return those values separately. Um, yeah, but for this demonstration, since we're not calling this from an external context, since we're just calling this locally, like normally this would be like a library contract that your financial application might call into to set a price for a given option. But for this demonstration, we're just going to call it from our local machine to have it output the console to console output the price. All right, so the compute all function is basically the implementation of the Black-Scholes formula. It's computing the discount um, from that formula. It's computing the square root of the maturity. It's computing the square root of the maturity times sigma, which is again the volatility rate. Um, it's computing the K discount, which is the strike price times the discount rate that we computed up here. Right here, I'm using this like exponent function. Um, what that is that's e to the x. So basically, if you remember from the equation, if I can pull it in, let's pull that formula in so we can look at it. Um, if you remember here, this portion of the equation here, this e to the negative r times t minus t. All right. E is the exponent, the Euler's number. Euler's number raised to the inverse of r times t. All right. And that's maturity is t. Right? That is how much time it has left to mature, the option. And then R is the rate of the return. We add the negative symbol in there, which is from the formula directory. And then, so we're basically just the EXP function here is given it to us by the decimal library. So we've got that e to the negative R times t. So that's that portion of the equation checked off. And so we're just going down the list, implementing each portion of the formula. And again, like if this is your first time seeing Black-Scholes, it'll probably fly over your head. But like if you walk through this example after this and follow through, you can see that we're just like peeling off different pieces of the function, computing it all together to get our final option price. So, um, yeah, again, hard to do this in a single session to explain fully what's going on, but pretty easy to follow along um, if you cross reference with the formula. Here we're using the square root function, which is also provided by the decimal library. So again, these are nice things that don't exist in Solidity. So we're able to do eat simple square roots. We're also able to do we're able to right here. I've got a cumulative normal computation where we're basically using this Abramovitz approximation error function, which is we're using this function to compute the cumulative normal distribution. Again, this is a statistics concept that is computing the likelihood that x is going to be x being the parameter passed in, x is going to be in this range. It's a probability function given the current state um, of the market or of the strike price and this and the current asset price and the strike price to basically say that what's the likelihood that this ends in the money. Um, so we're using these functions that are built in. So this is nice. We don't have to implement square root ourselves. We don't have to implement the Abramowitz approximation ourselves. We can just use the decimal library, which already has this common mathematical or statistical function implemented for us. And that's one of the benefits of Rust is that we're able to pull in these libraries that already have these complicated things implemented for us. And we're just able to import like a simple crate, a simple Rust decimal crate, and use that in our code. And it just simplifies things. It's very nice. Um, did I just Hopefully I didn't change anything. And then here's where we're computing D1. We're using the ln, which is the natural logarithm function. And that's from that formula over here. I don't know if I can put these like side by side, but yeah, yeah, hang on. Yeah. So right here, see D1 is being implemented right here. and we're just translating natural log. So this natural log of S over K, so that's S over K times the discount. This is what this simplifies to. Um, that's what this whole numerator simplifies to. Divided by the um, the square root of the square root of the maturity times sigma, right? So that's what we computed um, up there that was passed in. So then then we're then we're multiplying uh yeah, 1 over 2. Yeah, all this is just a simplification of D1 when you actually like distribute these terms out and then simplify the equation. It simplifies to this. So again, something to come back to, but note we're using natural logs, we're using Abramowitz approximation, we're using Euler's numbers. So we've got access to all these advanced math that we're able to just tap into to simplify our code. And we've only got like we're able to implement Black-Scholes in less than 100 lines of code. So let's go ahead and run it and showcase like what this looks like in practice. Okay, so um, if we go here, we're gonna pull up. I've already deployed this, but I'll go ahead and deploy it again. If I do cargo stylus deploy, um, I'm passing in the no verify option, which just basically says that we don't care about verifying this contract currently um, on Arbiscan. We're just we're working locally anyway, so it doesn't matter. And the endpoint currently is set to my local host at port 8547, which is the default port uh, that a local Arbitrum dev node runs on. And to review, if you go to docs.arbitrum.io, if you go to the stylus section, if we click over here and we click write stylus contracts, and I think we click run a stylus dev node right here, it's going to explain how to run a local Nitro test node that you can use to run a simulated Arbitrum environment locally on your machine in a Docker container, and um, that will just set up like a whole virtual L2 and L1 on your machine that you can just deploy contracts against. So, highly recommend you use that as you're developing on Stylus, and just again go to docs.arbitrum.io to get that. All right. Um, Going back to the code here. So we're going to go ahead and deploy this contract, and it's going to get deployed at this address. I'm going to copy that address there that deployed to. It ends in 821E. And I'm going to go ahead and set a local variable t- to that address. Okay. And that's going to enable me to then use cast. And cast is comes from the Foundry CLI tool. So if you don't have Foundry, I highly recommend you download Foundry. It's highly useful whether you're working with Stylus or just standard Solidity for making calls in your console against the chain, whether it's your local chain, a local chain on your own system, or or the Sepolia testnet or mainnet. So you're able to like run and call contract functions from the CLI. Again, if you go back to our workshop from day one, I went into that in a lot more detail. But for this one, we'll just go ahead and follow along. I'm using the cast send function. And the reason why I'm using send here, even though this is technically a read-only function that doesn't mutate state, I just want to show how much gas it costs to call this, right? And so for me to if I use cast call, it's going to do just a read only call to the RPC, and that doesn't use gas. So we're going to actually send a transaction on chain in order to show how much gas it costs to execute this transaction. All right, so we're going to pass in the RPC URL, and I've set that to a local variable called RPC. And then I've got a private key, which is just the testnet private key. Um, like when you click down here, you'll notice that in the docs it shows that a dev account is pre-funded with ETH on all networks. So when you run this locally, this address is funded with a lot of ETH, and this is typically the address you're going to use to execute local transactions against, and this is the private key for that address. When it's your private key and it's your funds, never show that private key to anyone, never publish a video, and never, definitely never put it on docs publicly listed here, but this is a doxed address with a docs private key that we simply use for testing purposes. So this is purely a test private key that's only useful in this context of local development for local Arbitrum development. Um, so the private key I've set to a private key variable in my console. And so I'm just going to go ahead and finish typing that. After you've got the RPC URL for cast send and the private key, we're able to then pass in the contract address, which I set to that local variable up here. And I'm just going to fill that in there so that it fills that in for me. And then I'm calling that compute function, which is this function up here. Since it's on public, I've basically said these are my public functions here. And I only have the one, as you notice, within this impl block. So I only have the one public function. It's called compute, and it returns an I256 and a U256 as a tuple. So it returns two values: one signed 256-bit integer, and one unsigned 256-bit integer. Okay, and right here we're using Solidity style syntax because this is, even Stylus. Oh yeah, I'm wrapping. I'm getting a top of the hour warning, but I'm wrapping this up. Um, we've got a 250 single. We got the tuple here, a 256-bit int and a 256-bit unsigned integer that we're expecting from the return body. We'll click and send. Okay, cool. And right up here, if we scroll up here, we're going to see that that equation only costs 63,700 gas to use, which is um, which I believe is less than a single like Uniswap call. So it's, we're not mutating state or anything, but but we are doing a very complex differential equation. That whole we're computing natural logs, we're computing exponent functions, we're computing square roots, we're doing a lot of math in that time frame. So for this to only cost 63,000 gas is a phenomenal deal. I don't think with even Solidity, if it was feasible to do within the constraints, I don't believe you'd be able to um, get the price below the low millions for Solidity. But you see here, it computed the call price for that option as $8.02. So the call option price should be $8.02. So to buy this option to bet that the stock price will be above $105 1 year from now, it just costs us $8.02 to buy that option. So you can see we're able to we only have to exercise the option if it finishes in the money. Otherwise, we just lose our $8.02. So um, you know, I guess we have to factor for the costs. We have to factor for the cost um, that the option costs. So really, we want it to be more than 113 to make up for the price of the option, right? 105 plus 8. So that's part of what Black-Scholes is doing. It's computing that the strike price plus the cost of acquiring the option is going to be, we're betting, like looking at the probability that it's going to end in the money um, 1 year from now. And yeah, I mean, more or less, that is the equation, and that's how it works. And um, oh, okay. Um, yeah, we're wrapping up. Oh, sorry. um, Yeah, so that's what I wanted to showcase today is like how you can do advanced on-chain DeFi, just low tens, just a few tens of thousands of gas where you're able to do this advanced on-chain math and unlock like the future of on-chain finance, which is like these advanced financial applications that have yet to be explored because the EVM is quite limited in the amount of memory and computation that gives you. It's very easy to hit Stack Overflow errors. It's very easy to like run into walls with implementing this complex math. So it's um, it's really cool to see that Stylus even, and this is an uncashed contract, so it's really cool to see. You can also cash this to get additional savings, but it's really cool to see that just a basic implementation is very simple to do using, using a Rust library, and then and getting access to that tool. So just wanted to showcase that as a cool application. This equation, set off trillions of dollars of market trading, 40 trillion in monthly volume on traditional finance markets. Would love to see more of these types of instruments be represented on chain. We haven't seen too many on-chain options implementations. I suspect it's because the math is very difficult to do in EVM. But with Stylus, it's something worth exploring, and would love to encourage y'all to explore some of that. And just to see what you can do with more power at your fingertips. But that is all the time we have for today. I want to thank y'all for your time. Um, thank you for tuning in. And with that, we'll wrap it up and call it a day. Thank you.